How do single-photon detectors measure photonic qubits? Imagine trying to catch a tiny, glowing spark in a dark room. That's similar to how single-photon detectors work when measuring photonic qubits. These detectors are essential tools in quantum computing hardware because they can identify individual photons that carry quantum information. Photonic qubits are encoded in properties like polarization, phase, or the time when the photon arrives. To measure these qubits, the photons are directed through optical setups such as polarizers, beam splitters, or interferometers. These devices help project the qubit onto a specific measurement basis. Once the photon passes through, the single-photon detector steps in to see if a photon is present in a particular output mode. If it detects a photon, it reveals information about the qubit state. There are different types of single-photon detectors used in quantum computing. One popular type is the superconducting nanowire single-photon detector, or SNSPD. These detectors operate at very cold temperatures, often below -270 degrees Celsius, to achieve high detection efficiency. They are known for their low timing jitter, meaning they can tell exactly when a photon arrives, and they have very low false detection rates, called dark counts. Because of these qualities, SNSPDs are widely used in photonic quantum computing setups. Another common type is the avalanche photodiode, or APD. These can work at or near room temperature, making them more convenient. APDs detect single photons by amplifying the tiny electrical signals generated when a photon hits the detector. While they are easier to use, they usually have lower sensitivity and higher noise levels compared to SNSPDs. Still, ongoing improvements are making APDs more suitable for quantum applications. There are also visible light photon counters, or VLPCs. These solid-state detectors operate at low temperatures and can count the number of photons in a pulse. They produce electrical signals proportional to the number of photons detected, which helps in more complex quantum measurements. In quantum computer architectures, measurements often happen on highly entangled states called cluster states. The single-photon detectors identify whether a photon is present after passing through the measurement setup. This process collapses the quantum state into a classical outcome, which is then used for further computation. Instead of performing complex multi-qubit gates, quantum algorithms often relying on sequences of these single-photon detections to process information. However, there are practical challenges. Detectors need to minimize false positives, maximize the chance of detecting real photons, and operate at temperatures compatible with the overall system. Advances are ongoing to develop detectors that work at higher temperatures and can be integrated directly onto photonic chips. This integration aims to reduce losses and improve scalability for larger quantum systems. To sum up, single-photon detectors measure photonic qubits by turning the quantum information carried by individual photons into electrical signals. Their sensitivity and accuracy are vital for reading out and manipulating quantum information in photonic quantum computers. These detectors are the bridge between the quantum world of photons and the classical signals that computers can process.